Hello, good morning everyone. I will give a speech about how you can secure your job by implementing MPLS VPNs. I will have some more words at the end about this title because there's a story behind that. So my name is Roger Gotschbonne, and as you can see, I'm coming from Switzerland. You can see that from the email address. So CH means Switzerland and not China. So the first thing is why did I have an idea to talk about this stuff? This talk should show some lessons we learned when implementing and running an MPLS VPN network. Nextra Switzerland, where I'm working for, is running a national MPLS VPN network since about 2.5 years. It's quite a small network because Switzerland is quite small, so about 30 POPs. Everything is Cisco-based. Then the Nextra group, which is has a pan-European MPLS VPN network since about 1 year. So this means that all the Nextra companies in all countries in Europe are connected together, so we can build pan-European VPNs for the customers. And because all these Nextras are autonomous companies, so every Nextra can basically do what they want, and so this is where it starts to get really interesting, or where the fun starts. I will not discuss whether MPLS is a good thing or not. I think there are other people who can do that much better than I can. So, lessons learned. The first and the most important lesson we learned is this one. A reload a day keeps the tech away. No, of course I'm just kidding, because to tell you the truth, even a reload won't help you. So, no, this was just another bad joke. I'm sorry. I think the most important thing about this whole MPLS VPN stuff is that you get some very interesting features which you can sell or try to sell to your customers, but it makes your life much more complicated. So for the operation people, they have to start to think about BGP, about labels, all this stuff. So for them it's really hard to get into this new MPLS VPN world. And also for the engineers, it can be very difficult because everything is much more complicated. So you will need a lot of training and more training to do that. And this is also where the job security comes from, because once you understand these things, they cannot just fire you because they need someone who can engineer and operate all this stuff. So I would like to start with a short overview about our service architecture, so how we build VPN services. This is just a way you can do it. Of course, you have there are other possibilities. So what we are doing is that the whole service to the customer is based on this MPLS VPN routing realm. So this means that for each value-added service we have each service has its own VPN. And also each customer gets his own VPN. And then customers, if the customer wants a service, then the service VPN and the customer VPN gets interconnected. So the problem now is that if you look at what you can configure on a Cisco router, you will see that you can configure very, very complex VPNs. So basically you could build a completely different VPN for each customer. So you could meet the customer requirements, but then the problem you have is that once you have a lot of customers, every customer has another VPN which looks different, so it will be very complicated to operate that and to troubleshoot. So what you need is, you need some kind of structure in that, you need a service architecture, and so what we did is we defined some building blocks. Actually, these are 4 building blocks. And each building block is quite simple, easy to understand, and then all you can do, all you can do is just put these building blocks together. So you can build more complex solutions for a customer, but you still have only 4 building blocks. So once you understand the 4 building blocks, you understand all solutions you give to the customers. I would like to explain this a little bit more. So these building blocks are like Lego bricks. So you have 4 Lego bricks, you can put them together. The first one is quite easy, it's a full mesh VPN. So each side down there can see each other's side. Very easy. The second building block is a hub and spoke VPN, which is a little bit different. So the spoke can see, or each spoke can see the hub can see all spokes, but one spoke cannot see another spoke. It's also quite easy. The problem you will have here is you should be very careful about default routes. As soon as you have a default route on the hub, it could happen that the spoke sends some traffic to the hub and then the traffic goes down to the other spoke. So then one spoke can see the other one. So as soon as you have a default route there, you need some other mechanisms to prevent one spoke to see the other one. So the third Lego brick is a conduit. A conduit basically is a pipe, which is between, for example here, between a hub and the resource. So when you interconnect the hub with the resource, it goes through a pipe. And on this pipe you have some control over the traffic. For example, you could configure how many megabits per second can go through that pipe, or you can configure an access list or whatever. And the fourth Lego brick is an adapter. And an adapter is something which sits in a pipe. And this can be, for example, a firewall, it could be net or something else. So with these 4 building blocks, I can now start to design some services. So one thing you can do is a customer can have multiple VPNs. So in this example, the customer has 3 sites. Each site, or these 3 sites are connected with a full mesh VPN, so each site can see the other side. And there's also another hub. So these 3 sites are also spokes and can talk to the hub. So what could you use that for? If the company has 3 sites, so they can see each other, and now they need some internet access, so they get a hub and spoke VPN to the hub. And on the hub, or at the hub side, there's a conduit, and on this conduit there sits an adapter, which could be a firewall, which is managed by the ISP. So the ISP can manage the firewall here for the customer, and the customer just can send traffic around and has access to the internet. Another thing you can do is this solution here. You again have 3 sites, and one side is the main site from the customer, where his headquarters is, and the customer needs internet access, but the customer says that he doesn't want a managed firewall from the ISP, he would like to have his own firewall on his side. So you can build something like this, so that all the traffic goes to the headquarters, and then in the headquarters through the customer firewall, and then from there to the internet. Another thing you can think about is to have a system where you have load sharing and also redundancy. So the main sites from this customer are connected via 2 lease lines to 2 different POPs, and you can build it in a way that you have load sharing and also redundancy. So if one link or one POP breaks or one router breaks, there's still some connectivity. Another thing you could do is this is called disaster recovery, or we call it disaster recovery. So for example, for a Swiss bank, if they have a main computing center and they have an exact copy of this computing center in another city, so they can configure it with exactly the same IP addresses, and both computing centers are configured as a hub. And so normally all the spokes are talking to POP A, or to the computing center connected to POP A. If this one breaks, the other computing center can take the work over. So the sites or the customer sites shouldn't notice anything, so they just have connectivity to the same IP or to the boxes with the same IP addresses in the other computing center, in the backup computing center. And of course, you can also do some things with a dial. So, for example, dial backup. So, if a customer site, the link breaks, they can dial in automatically and have exactly the same connectivity as they had before. Perhaps a little bit slower, but they can reach the same site again then. And then the next thing you can do, you can make this a little bit bigger. So here you can see a customer A, which has full mesh. Customer B has full mesh, and then there are two hub-and-spoke VPNs connected through two conduits to a so-called partner net. So they can have some connectivity between the two companies. And this, you could also think that this partner net is another ISP. So with this system, it's possible to connect one customer, which has one ISP, with another customer at another ISP. So you can start to build VPNs between different ISPs. This is what Nextra is doing in Europe. When one customer sits in, let's say in Switzerland, is connected to Nextra Switzerland, and this customer has some sites in, let's say, Germany, which are connected to Nextra Germany, and so we can interconnect them. Okay, these were a lot of slides. I hope you're still alive. Okay. Now I would like to go to some very specific, or to tell you some very specific things about problems or issues we discovered when we implemented this MPLS VPN stuff. The first thing is route reflectors. So this whole MPLS VPN stuff is built up in BGP. So this means that you need some BGP sessions within your network. And of course, you do not want a full mesh BGP. It's the same as in the IP world. You will have route reflectors. And so you should use two route reflectors for redundancy, of course. And then the other point is that at the beginning we thought that, oh well, we have IP version 4 route reflectors, so for the VPN stuff we could use the same boxes. No problem with that. But then if you configure that, then you will notice some things. The first thing is that if you have IP version 4 routing instabilities, if the internet is flapping or you of the internet is flapping, then these route reflectors will have a lot of work to do, and this could impact your VPN connectivity because the VPN route reflector is the same box. The other problem we discovered is that if a provider edge router is reloading, then he is rebuilding the VPN, the BGP sessions, and if you use the same BGP session or the same route reflector for IP routes and for VPN routes, what will happen is that first you learn all the IP routes. So this means that first you learn 100,000 IP routes, and during this time you have no VPN connectivity. So this is also bad. I think there should be a knob somewhere now or in the future, don't know, where you can fix this. But one way you can fix it is to have separate route reflectors for the IP world and for the VPN world. And so when your edge router reloads, you have two BGP sessions which came up at the same time, and so you will learn the VPN routes also from the beginning, and so your connectivity is restored much faster. So this means that you need more route reflectors, and one idea you can have is to use core routers as route reflectors, because in an MPLS world the core router hasn't to do too much work. It's just so you could use it. Another thing is a lot of people are, or there's this RD, this route distinguisher, which makes the VPN route unique. So a lot of people are saying, yeah, you need a different route distinguisher per VPN. But this is not really true, because as soon as you have route reflectors, this will break load sharing. Because if you are doing load sharing, you need two routes, to the same destination for the same IP prefix. And if you use the same RD, then the route reflector will see these two routes and will say, oh, well, I have two routes which are identical, so I will choose the best one and drop the other one. And then your load sharing is broken. So what you need is one RD per VRF, or per, not per VPN. This is something you should think about it from the beginning. And another small tip is, if you are using route reflectors, you should check your next hop of the BGP routes you get from the route reflector. We had some cases where the next hop was set to the route reflector, which then leads to some very interesting traffic patterns. So it means all the traffic goes to the route reflector, which is quite bad. Another very important thing is the story about baby jumbo frames. So if you are using MPLS VPNs or MPLS, then you have these labels. An MPLS label is 4 bytes long. So this means that on the link you have an MTU. If you have a label, then the IP packet gets decreased by x times 4 bytes, because you need also to transport these labels. And of course you have path MTU discovery, so the sender will detect that the MTU is lower and will send a smaller packet. But it seems that path MTU discovery sometimes is broken. This can be through some operating system implementations who cannot handle this correctly. Could also be because a lot of firewall administrators are a little bit paranoid and are thinking that ICMP is bad, so deny all ICMP packets. So path MTU discovery doesn't work. And of course then the customer will blame you of that, because they will say, yeah, before we were on this MPLS network everything worked fine, and now it doesn't work anymore, so it's your fault. So what can you do? One thing you can do is you can configure that. So you can configure on the link a bigger MTU. For example, on Ethernet you can say that the Ethernet should be able to send 1508 byte long packets. But before you migrate to MPLS, you should make sure that all your routers, the interfaces, the switches, and whatever you use are able to support these baby jumbo frames, or are able that you can use these commands. Otherwise, you will start to build your network, and then you will discover that your switches are not supporting this, and then MPLS VPN will just not work. Another nice thing is LDP, the Label Distribution Protocol ID. We had the case where after a crash, a core router stopped forwarding any traffic. Nothing worked. So we checked the configuration on this box, and the only strange thing we found was an interface loopback 99 with description test with an IP address of everything 2. And it seemed that someone was playing with this box. Well, it's not a good idea, but at the end, this loopback shouldn't do anything bad. I mean, it's just a loopback, it's not in the routing, nothing. It shouldn't be a problem. But then the problem is that in LDP, you also have an ID, an LDP ID, like in OSPF, and the router will choose the highest loopback IP address. But unlike in OSPF, in LDP, the ID has to be reachable. So this means that in OSPF you can choose whatever you want as an ID as long as it's unique. But you will never see an IP packet with the OSPF ID in the header. But in LDP, the routers will send TCP packets to the other router and will use the LDP ID as destination address. So this means that the LDP ID of 222.222.222.222 was not in the routing, so the ID was not reachable, so the LDP session was not coming up, so the router didn't have any knowledge about labels. So it's really important that you configure all the LDP IDs manually on the box. Then you won't have any problem with that. So the next thing is traceroute. Traceroute is no longer your friend. Why? Yeah, this is a network. You can see 2 customer sites at the left and the right side, and the MPLS core network in between. And now let's assume that here the network is in some way broken, doesn't work there. So the customer cannot send packets, and then what you do normally is send a trace route to check where the problem is. And if you do a trace route, you will find that the edge router is sending you back an answer, but then you will see only stars. So this means the trace route stops when it enters your core network. And so you have no idea where the problem really is, because normally in the normal IP world with the trace route, the problem normally is at the last hop you can see, or perhaps on the next hop when he cannot send the answer back. But with MPLS it's quite different. You don't have any clue where the problem is. Now, why is that? Well, if you think how trace route works, you send an you send an UDP packet with a very low TTL, and then the router lowers the TTL by 1, and then the packet TTL is 0, the packet dies, the router sends back an ICMP time exceeded message. But now here the second router should send this ICMP message back. And now what can he do? He cannot use the routing table to send the packet back because it's a core router. It doesn't have any idea about VPN routing. So the only thing he knows is the LSP where he gets this packet from. And now the LSPs are unidirectional, so it means it's not possible to send a packet back through an LSP where you receive the packet because it's unidirectional. So the only thing the router can do is send the packet back or through the same LSP where he got the packet. So this means that the ICMP time exceeded message goes through the same LSP, through the whole network, but then this LSP is somewhere broken, or the forwarding of the LSP. And so the answer never gets back. And this is the reason why the trace route stops at the first hop from your network. This can be even worse if you start to use MPLS with our different ISPs. As in this example, I have two ISPs and the transit ISP in between. So what you will have is an LSP from the first edge router to the last edge router. And now if let's say the forwarding is broken there, still the trace route will stop at when it enters your network. And here in this case it's even worse because you have no idea whether the problem is within ISP A, ISP B, or within the transit ISPs, or in the peering point, or wherever. You just don't know it, which is quite bad. Another thing we discovered is that a customer sent us a trace route and said, well, this is quite bad. If you look at this trace route, what you can see is that the second hop, or the first hop, has a TTL from 0.04 milliseconds, which is quite good. And then the second hop already has a TTL of 100, round trip time of 100 milliseconds. And this now is really strange because I wrote it there where the routers are sitting, and the hop 2, 3, and hop 4 is still sitting in Europe, and hop 5 is sitting in New York. So normally what we see in Europe is that hop 5 should have a high round trip time because the packet has to go to New York and back, but hop 2 to hop 4 should also be 10 or 20 milliseconds, not more. And then the customer said, well, this trace route is really bad, the network is bad. What's happening here? A professional troubleshooter was looking to this problem, and here's the answer we got. And will take some time to read through it. But what they're saying is, well, trace route is using IP options, and if you have packets with IP options and your router processor has a lot to do, then it will be delayed and such things. But of course, this is wrong. What is happening here is basically the same what happens before when the trace route stopped at the first hop. So the trace route packet enters the network, and then the first hop wants to send back the ICMP time exceeded, but because he doesn't have any routing information, he has to send the packet forward through the whole MPLS network, through the other edge of the MPLS network, which is in New York, where our upstreams are, and then the packet goes through New York and then back. So each trace route, which is in the network, will go to New York and back. And this is why you can see all these high round trip times there. But of course, this is not a big problem because you can explain to the customer this or what happens, and the customer shouldn't care about that because the production traffic is not. This doesn't happen to the production traffic. It's just for the trace route where you can see these strange things. But then the customer sent an email back with this one and said, well, it's not true, because here at hop 2 it's 100 milliseconds, but hop 3 and hop 4 is 15 and 16 milliseconds. So it's not true what you told me. And the reason for this one is quite easy. It was just a bug. Okay, now I would like to go into some security considerations, but no religion wars, please. So one thing is configuration integrity. If you build MPLS VPNs, then the customer wants that his traffic in his VPN stays in his VPNs, it doesn't go into other VPNs, of course not. But sometimes bad things can happen because of software bugs or because people are typing too fast. Are these minutes or seconds? Minutes? Oh, okay. So I have 10 minutes left, not 10 seconds. Thanks. Oh, that's good. So, and of course, this can be very, very dangerous if you configure bad things. And the problem is not when you break connectivity, because if you break connectivity, the customer will call you up, or your NMS station will no longer see the customer router, and then you will get an alert. No problem with that. You can fix that. But the bad thing is if you have too much connectivity, because, well, the customer will also detect this, but perhaps in 6 months. And then you have a problem to explain why this is. So you need some sanity check tools to check your configuration or to check the routes. And here I have some examples I discovered in our network. So this, well, it's a little bit faked, so it goes onto the screen, it fits on the screen, but it's I really found this on our routers. So this is how it should like. You have a router BGP and then some usual iBGP stuff. Then you have address family for a VRF, let's say green, and here is the BGP stuff for the green VRF. And for example, you have here redistribute RIP, because we are talking RIP to the customer router. This is how it should look like. But now this is what I found on the router. Router BGP 88 redistribute RIP. So it was just because here the only fault is that the command is right, but it should be under the address family for this VRF and not under the global router BGP command. This can be quite bad. Well, we don't use RIP in our backbone, so it was not a real problem. Okay. So let's look at the RIP configuration. Router RIP, there's nothing configured because we don't use RIP in the backbone. But under an address family, we use RIP. So let's say there we have redistribute BGP 88. So the BGP routes in this VRF or in this VPN are then redistributed into RIP and sent to the customer. This is again how it should look like. Now, what I found on the router is this one, router RIP, redistribute BGP 88. So this means the whole BGP information is redistributed into the global RIP, which is also not so a problem. But now, if you start to think that what could happen if you're using addresses from the 62/8 block, because on the RIP you have this network command, and this is still classful. So if you use 62 something there, this would mean that the network command is valid for the whole 62/8 block, which would mean that on all your backbone interfaces, you will start to talk RIP. And if you combine this one with the previous slide, what then could happen is that you'll have your global BGP process, you redistribute it to RIP on one box, then it goes via RIP to the other box, and from there to BGP again. So this can be very, very ugly. And so this is another reason for very, very good filtering at the edge. So if you have this problem internally, at least it won't go out to the world. We were also thinking about pre-configuring all the possible redistributions with a route map which says deny all. So if you configure then the redistribute again, it's already there with deny all. So another thing to add is secure your edge router VTIs. What you normally have on a router is you have an access class 99 and some authentication method, and you have some access lists which are saying, well, only from the NMS box, which is one IP address, and from the backbone links, you are allowed to telnet to this box, and from no other IP address. So this is more or less secure. But now, imagine what happens if the customer sends you a host route for your NMS box. I mean, in the normal world, the customer cannot just send you a route because you will filtering all the routing updates. But if you are providing VPNs to the customer, then if it's a VPN, it's private, so the customer basically can send you whatever route they want. So they can also send you a route for the NMS box, and what will happen then is that he can telnet to your box and try all the passwords, which is also a very bad thing. So you should start to think what you can do against that. And here are some ideas, but you could, all these ideas are basically, you could think, well, I could use host routes for the NMS station, but this won't help you because if the customer sends you the route via RIP is better than IPGP, so the customer will win. You could put host routes to the null interface on all VRFs, but then you cannot access the customer CPs anymore, so you cannot manage them. Or you could also start to filter routing updates from the customer, but also this is bad because then the customer doesn't have full connectivity, so he will be limited or can no longer use some certain IP addresses in his network. So what you should do is the following. Let's say this router has a loopback address 1111, so you should start to use another access list to secure the VTIs, an extended access list where you say that from the NMS station and from the backbone links, you can telnet to the loopback, and also from the NMS station and the backbone links, you can telnet to all the IP addresses of the interfaces which are not towards the customer, so just to the interfaces towards the core router, which are not in a VRF. So what will happen then is that even if the customer sends you a host route for the NMS station, he will not be able to telnet into the router because this IP address 1111 is not in his VRF, and also the IP addresses of the interface towards the core are not in the VRF. So he can no longer telnet to your box. Okay, that's it. I just saw that I have still 1 minute. No. Yeah, okay. Or I need 10 more seconds. I have to admit, I gave this presentation of the LARITE meeting in Prague last autumn, and there the title was still true. And I was very proud that Nextra back then said, laid off about 40% of the people, and I survived. And I said, yeah, well, it's because I implemented MPLS VPN. But then later on, they decided to close down the whole Nextra Switzerland. And so, even if you have implemented MPLS VPNs, you won't survive that. Thank you.